This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. All right, so we're going to finish off our discussion on discrete dynamics. If you have the workshop this Friday, you will need the stuff that we cover in this lecture. If you have the workshop next week, obviously, you will need it as well because you are programming the Kabuki robot with a state machine. Okay, so you'll have to be able to be mapping out your state machine. In particular, when it comes to doing the project work for the subject, which is the obstacle course navigation, you'll need to provide a full state machine description of your algorithm for controlling the robot and also reachability analysis as well, okay, which is what we'll see a little bit later on. All right, so what happens when you turn on a system, right? It goes to some initial state. We normally use a double circle or a bolded circle to indicate a default state. But what about default transitions? If you have a controller of some sort and it has a lot of inputs and you have to specify every way out of that state, it might get overly complicated to actually show that you remain in that state. So sometimes you'll see on diagrams drawn these ghost transitions. They're called ghost transitions because they have dotted lines, and they're just called default transitions. And a default transition looks a little funny here, right? In that it doesn't have a guard and it doesn't actually specify an output. And all that does is basically it's enabled implicitly if no non-default transition is enabled. So in other words, if this condition here is not met, right, up and not down, so up being present and down not being present, then we implicitly stay there. So there's a default transition to stay in the state. Okay, and that's essentially what state machines do. They have memory in that they remain in the same state unless otherwise told to go somewhere else. So this default transition is enabled when this condition is not matched, right? And then therefore it loops. Sometimes you may see these things written in state diagrams as, you might see just as true sitting there with a slash with no particular output, and that's telling you it's a default transition. Okay, so that's enabled if another guard is not satisfied. All right. So let's have a look at a traffic light controller, so something a bit more complicated. And this is an example of a model of some system with discrete dynamics that has as inputs time r, and then the other colours. I've got my ordering wrong. Yellow, then green. So time, it's moved. So time red, time yellow, time green, and also there's an additional input called is_car. There are three outputs which will signal the traffic lights. Let's do these in order. R, Y, and G. Okay, now, in this case, these are all pure signals. Okay, so they're either present or absent, that's it. And the outputs are present or absent as well, in order to drive the lights. And we start off by investigating this state machine diagram by looking at where we start off at. Okay, so we're starting off in the red state here. Now, we do not transition out of this state unless this guard is satisfied. So in this case, time R and is_car are both present. So that's essentially, well, there's some sort of timer that's controlling these elements here, and once that is set to be present, and there is a car which is detected probably by an external system, we just then obviously react and go into the green state. Now, while we're in the red state, we are continually holding sig R down, right? We're keeping the red light on, and immediately upon this guard being satisfied, we enable the green signal by setting it to be present. We go to the green state. And notice there's a nice symmetry in these three states, right? We have that little default transition which says keep doing that unless you get a guard satisfying out of there, right? So in other words, time G or time yellow to get out of the green or the yellow states. Now, state machines get very complex. You know, you may design a state machine, might have 50 or 60 states in it. And showing this implicit loop back, right, in other words, the default transition, can get very messy. Essentially, every state would have to have some sort of loop back on it, and it looks terrible. So what we typically do is we only show these loopbacks, these default transitions, if they're guarded in any way. So there's some restriction in holding it there in some sense, or that they produce outputs. Okay, so in other words, here we are actually, right, via that default transition, even though it's unguarded, always holding sig_r as being present, right? So, telling the lights to basically be red. Okay, so this is, some of you may have learnt to put state outputs inside the bubbles. It's kind of how you mask doing these default transitions, right? You pop the output inside the state. But we're doing a bit more general way of doing it, which handles Mealy machines a bit better, that we use the default transition with an output. Okay, so it's fairly self-explanatory. The output's persistent in a state, and once it gets out of that state, it changes the output to another colour. As an example of a setup where default transitions don't need to be shown is a little heating cooling example. Now, if we skip back a few slides, this is what we had last lecture. We had a temperature controller that migrated between the cooling and heating states if the temperature got too low, below 18 degrees or equal to 18 degrees. And it remained in this state while it was less than 22. And when it got above 22, it went to the cooling state. This was a very simple setup where it had a real number as input and as an output was just a pure output heat, right? We can actually eliminate these transitions, right, back from a state back to itself if we do something a little clever. Let's modify our design. So instead of having a discrete dynamic system with temperature as input, which is a real number, and just one heat output, we're now going to have two outputs. Heat on and heat off. And they're both pure outputs again. What the difference here is that, well, just look at the state diagram. Immediately we actually don't need those loops in states. Now why is that? Because implicit is now that the controller that this temperature, the heating unit or whatever, that this temperature controller controls only reacts to the presence of these two signals. Okay, so you actually have to set heat on to make it turn on, and you have to set heat off to turn it off. It's like a set reset mechanism on it. Back in our earlier case back here, we actually in the heating state had to explicitly hold heat on. Okay? So when the temperature got low, heat was set and you stayed in the heating state while the temperature was still heating up, but you still kept the heat output on. So you needed this loop back. Imagine if we didn't have that there, right? If we didn't assert this, heat output in the loop here, it would go off, right? It reacts, sets it, and when it's here, well, it's absent again. Okay, so it shows you that there are two ways, or at least two ways, of designing a state machine. This one has an extra output. This one relies on a sort of like a set reset type heater unit. The other one was just basically, well, a transistor could have driven it, right? While the signal's present, you're heating, and when it's absent, you're not. But we now don't need to have these explicit default transitions inside the states. Okay? So as an exercise, you could apply the formal procedure of looking at the input-output space and the update space for this and write it all out. And indeed, we'll do that a little bit later on for some other examples. Okay, so it's not unique. There are three definitions that we have to make when we are going to start analysing FSM models, called stuttering, receptiveness and determinism. And I'll save the best till last. Determinism is the fun one. So what's a stuttering transition? This is the default, if you like, explanation of it. I might turn it into some other words. So it's a default transition that's enabled when inputs are absent, that does not change state, okay, and that produces absent outputs. Okay, so how is a state machine, how is that even a transition? If it's a default transition, inputs are absent, does not change state, so it's looping back to itself, and produces absent outputs. Now, stuttering transitions make sense for time-triggered FSMs. If you think about, if you know a little bit about underneath how an FSM might work, there's always an update going of the state. If you think about how state machines are broken up into like a next state logic and some state memory with flip-flops, those flip-flops will keep loading that next state no matter what. Okay? Even if the next state's the same thing and all the outputs are the same, it keeps just loading it into the shift register or the flip-flops or however you're storing the state. So we call this a stuttering transition. It's a transition, but it's not a transition, right? It's happening, but it's not. So it's like it's happening in hardware, but on the FSM diagram, it's not happening at all, right? There's nothing, it's not moving around. Okay, that's why we say it's possibly implicit, default transition. Okay, so it's generally, as I said, time triggered. It's when a clock comes in. Now, what about receptiveness? So basically receptiveness means when in a particular state, you always have a way to go, exit the state. So all FSM should be receptive, right? That some transition is enabled for any of the input values, including default transitions as well, right? So if you've got implicit default transitions, because you might think about it as a time-triggered stuttering model, then that's okay. Then it's always receptive. It's always going to be doing some state update, even if it's updating itself with its own state. You know, it's just loading the next state being the same thing. So receptiveness and stuttering transitions are important. An example of a receptive, receptive state machine would be like a fire alarm, right? That it's sitting there essentially doing nothing, stuttering away. Probably it's a time-triggered system. And then as soon as someone pushes the button, it responds to it, right? It has a way out of some idle state. Lastly, and we're going to focus a bit more on this because this is where it gets really interesting, to do with abstraction, determinism. So what we mean by determinism means in any state, for all input values, you've only got one possible transition enabled. Okay? So, you know, you can have complex state machines that may, out of one bubble, you might have 5 transitions, but at any one time, only one is enabled. What happens if 2 are enabled? Well, we'll find out. Okay, it's called a non-deterministic FSM. And you might think that that's not a good thing, but it is for an abstraction, for abstraction purposes. Okay? All right, so these are our definitions. And I'll expand about the deterministic part. So an example of a non-deterministic FSM, I might actually draw one as well, is like a little car detector system here. We typically draw all our stuff in black and white, but we use something else, another colour, to indicate state transitions that can both be met at the same time. The conditions can both be met at the same time. So for instance, here in the no car state, we have some loop back. The guard is true, so that's always enabled. But sometimes via this other signal, right, if this signal's absent here, right, that it could also go to this other car state. And that makes things tricky, right? What does it do? On the diagram here, there is no information to tell you what it does. Which one should it take? Right, if both conditions are active at the same time. So typically, what happens here with these transitions is they're hiding something from you. That underneath this FSM, there is something going on which will generate these signals in a strange way and get the machine to go in a particular direction. I'll give you a more concrete example, and this one ties in with our traffic lights we'll see in a minute. So let's look at a traffic light system, but we want a pedestrian button. So we're going to do the following. We're going to model what happens when a pedestrian can control the traffic lights. So I'm going to I'll give you the 3 inputs. Sig R, Sig G, Sig Y. Just the 3 traffic lights. Let's say they're pure inputs. All right, so they're just telling me what state the light is in, basically. And there's only one output, and it's going to be pedestrian. It's also pure. Now, this is actually going to be a model of pedestrians arriving at a set of traffic lights. How on earth do you model that, right? It's essentially an event that you have no control over, right? People just turn up. Sometimes people will turn up, not push the button. Okay? So how are we going to model that? First up, for reasons why you can investigate as a problem in the textbook, but we're going to start off in the crossing state. And upon sig G, so the green signal, we are going to go to this state called none. Now, this is kind of a strange state, right? And we'll see why. It might make more sense where we have this state in a minute. There's going to be another state called waiting, right? Which indicates that there's a pedestrian waiting there. And to sort of fill it out in a funny order, because it might make more sense, we're only going to go to the crossing default state when SIG-R is asserted, right? So when there's a red light for the cars. It's another thing we've got to think about. Okay, so what happens between here and here? This state here is going to indicate that there's, something has triggered, a pedestrian has arrived, basically. There's an external mechanism that's doing that. That's not part of our inputs and outputs here. It's like an environmental condition. Okay? It's like thinking about this black box representation where we've got some inputs and outputs, but the environment can change as well, and it's not a mapped input-output of the system as such. Okay, so I'm going to draw here. We're going to sit here in this none state. It's going to be true and have no output associated with it, and it's just going to be there. So you're stuck in that state. That's it. You're stuck there forever if you get there. But I'm also going to draw a loop, transition, across to the waiting state. And this is also true. And when that happens, we assert pedestrian output. So we trigger that there's a pedestrian waiting. Okay, so we go to the waiting state, we wait for SIG-R to go off, and then we can let them cross. And so this is clearly a non-deterministic system. If we're in this state, what do we follow? Do we follow that true guard there, or do we follow that true guard there? Which one do we do, right? We don't know. Depends on the environment. There is no information provided there, right, as to how that transition will happen. Now, if you think about it, what that's essentially doing is it's hiding the fact that there's something happening. Something in the environment is going to cause it to go to here. All we've said is that we don't know what that is. That's a nice way of sort of saying it, right? We've made both of these transitions both guarded with true. Okay? It might sound a little bit weird, but when we look at the traces and things like that, it might make a bit more sense. Okay, so what we do with non-determinism is we are abstracting stuff. Okay? We are saying there exists a path to get from none to waiting that we cannot, well, we don't know what the conditions are for getting there, or we don't care so much, just that there can be a path to get there. Okay? It's like we've removed information from there, right? We've removed the information that tells us the transition that goes from there to there. Why? In this case, that could be a stochastic model or something weird, right? Where, depending on the time of day and the weather and whatever, will give you a probability of a pedestrian occurring at a given rate over a given time or whatever. It's some more complicated model. But we just know that when that transition does happen, then we go into a deterministic pathway in terms of setting the lights to cross. And we also set the output to be pedestrian. Okay, so non-determinism is actually quite useful because it hides things. It models unknown aspects of the system in a way that you don't need to know the details about. So, for instance, an example that might be tied to doing the robot navigation is how the environment could change a robot's orientation. You may not know the mechanism for how that happens, just that if it does happen, you need to go to a state to counteract that. Okay, that's another nice way of thinking about that, right? You've still got to draw out a state diagram to show how the robot responds, but you might not know how it gets in that particular state. So you do a non-deterministic model for it. Why else would you use non-deterministic FSMs? You're essentially reducing the degrees of freedom of your model by hiding the mechanisms that provide those transitions. Just dumbing them down, having two true guards, you are reducing the degrees of freedom. Another nice way of stating this is, and this happens typically when you're doing safety analysis on a state machine. If these are state machines that are controlling life-threatening machines and that sort of stuff, or, you know, flight controllers and all of that, you need to show that it is possible to get between states, right, as a potential thing. So it's almost like saying, well, there exists a path to get from here to here, but I don't quite know what the condition is that allows that, and I don't know the mechanism for it, but it's possible. Okay? That's very important for safety analysis. And sometimes when you're designing FSMs, you're actually designing them from a very non-deterministic way like this. You start off with all red arrows all over the place, and then you start filling in the details about what makes those transitions active. Okay, so I'll show another slide that shows about compactness of non-deterministic FSMs over deterministic FSMs. Now, the thing about FSMs is that they represent possibly infinite behaviours in a finite diagram. Okay? A behaviour of an FSM is like a sequence of things happening, right? Think about it, right? You're observing the behaviour of something. There are a sequence of steps that have happened to make that behaviour. So a behaviour might be, you know, a sequence of states that are followed. And if you sit there and watch the traffic lights all day, right, you'll see there's a behaviour, right? It goes red, orange, green, orange, red, etc. And you can look at how it's responding to the inputs. But how do you formalise all that? Well, the FSM shows exactly how that can be arranged, right? It shows you in a very compact representation how all the possible paths can go, but you've got to trace them out yourself. Another way of doing that is taking the FSM with all of its transitions and sort of flattening it out over time. And that's called a trace, or a computation tree. But in particular, following the paths around an FSM is called a trace. And it's neatly laid out for our traffic controller here, depending on the input conditions, the states that it goes to, and then how it branches according to the inputs. And so a trace is a record of input states and outputs in a behaviour. So this would be a behaviour here, right? An observed behaviour, and this is the trace of that behaviour. There's another trace here for another behaviour, and there's another trace here for another behaviour, another trace here for another behaviour. And this is called a computation tree. So we basically, we're exploring all the possible behaviours and mapping them out as these interconnections between the states over a sequence of inputs. That's also important, right? So here, if sig G was present, we go that way. If sig R was present, we stay there, obviously, over time. Okay, so we have to sort of enumerate over possible inputs as well, whether or not this sort of branches out over time. And the beautiful thing is FSMs are then suitable for a formal analysis like this. So for instance, and you can get computers to do the big computation tree of an FSM. So for instance, there may be in your FSM an unsafe state that you never want to get into by some reason, right? And you can do a computation tree for all the possible inputs and going through all the possible combinations of states and find out, indeed, that state is never reached. Okay? It can be computationally expensive to do that, right? To think about all the possibilities over time, it just becomes this big nebulous thing. But it's important for safety analysis. You have to be able to robustly prove that your state machine will not fail or end up in a state it shouldn't end up in. Okay. So we'll talk a bit more about reachability analysis later on in the subject. And that's a tricky thing to talk about whether or not states are reachable and how reachable they are and quantifying that in some way. All right, so why bother with these non-deterministic FSMs? They're great from a design perspective, starting out from scratch and laying out your sort of state machine in terms of knowing what transitions should be allowed and then working out the conditions on what they are a bit later, but also abstracting information away into your state machine. There's a really interesting result in automata theory. So this is the sort of stuff that we're looking at here. We're scratching the surface of automata theory. That a non-deterministic FSM has a related deterministic FSM that is equivalent in a technical sense. So, in other words, you can always find a related deterministic FSM for a non-deterministic FSM. The mic is just turned off randomly for some reason. Battery's dead. Great. No battery. All right, we've got to charge it up. So the caveat here is the deterministic machine, in the worst case, has many more states. It's actually pretty bad. It's exponential in the number of states of the non-deterministic machine. And check out the text for more detail, or have a look around on the web for this. It's a very interesting result. Basically, think about the non-deterministic FSM as clumping things together and losing information. And if you want to turn it into a deterministic one, you're pulling it apart again. Yeah? So if you've got a non-deterministic machine and you've got two transitions that are both true, for instance, coming out of it, but when you pull it out a bit more, it actually has one guard going that way, one guard going that way, right? It becomes much more complicated. And you can almost see that it grows in that sense. So going from non-deterministic to deterministic makes it more complex, which is against abstraction. That's the opposite of abstraction, trying to make it simple. All right? We won't go too much on about that anymore, but suffice to say that non-deterministic is great from a design perspective to be compact. Okay, so it's very simple. A deterministic state machine exhibits a single behaviour for a fixed input sequence. So you give it a set of inputs and it's always going to have that same behaviour, right? That's obvious. It's always got one path to follow given a set of inputs over time, right? But a non-deterministic system exhibits a set of behaviours. As I said before, we've got to actually map them out because you can maybe be able to spread at particular states depending on what's happened. And there's a couple of pictures here showing one behaviour of a deterministic FSM, and this is a non-deterministic FSM. Behaviour is a computation tree in itself. Okay, so it gets more complex to model that, of course. So simplistic FSM, but a more complex modelling behaviour. Because you've got the opportunity to go multiple paths for the same input sequence. Okay, so I hope that shows you how complex it is. It's like a computation tree within a computation tree of traces. It's pretty crazy. Now, one important point I have to make is that non-deterministic does not mean stochastic. Okay? Some people think the opposite of deterministic means, well, it must be stochastic then, it's probability based. Not in this case. Non-deterministic means we just don't know which path to follow. We have no further information on that, full stop. But you can actually get probabilistic FSMs as well. And they have transitions that are weighted by probabilities. Okay, so there's actually a higher chance of going one way than another way. For non-deterministic FSMs, you have no info. It's true, true. It's X, X, or not Y, right? It's equally probable going... well, you don't know. I shouldn't say equally probable. You don't know. There's external mechanism that's driving it. Okay. So in non-deterministic FSMs, no such probability is known. Indeed, there's nothing on the diagram that gives you that info. Okay, so to show you again the non-uniqueness, if you like, of FSMs. We had a very simple FSM last lecture that counted the amount of cars in a parking garage. There were some basic pure inputs up and down and one output that signalled the amount of cars that were present in the parking lot. And yeah, so it was also started off in the zero state. So we assumed that it was empty when the power was switched on, for instance. And every time you got a car coming in or a car coming out, you either count it up or down. The state is the output. It encodes nicely. We need a state to hold the number of cars, and that can then represent the output. So it's a discrete number here that represents the output. Now, there's also, we can also embed further information into the state machine, and it then becomes what we call an extended state machine. So an extended state machine augments variables inside the state machine. So in addition to inputs and outputs, we can also have variables that do some of the dirty work for us. In particular, this simple state machine, which looks like it's got a lot of repetition going on. I mean, come on, it's just a big chain, and if we have lots of states, it's going to be a big chain. We can actually boil that down to one state. So the size of this state space is 1. It's one state. It's not m states or m plus 1 or whatever the other diagram was, but it's just 1. Okay, what's the difference here? Well, it's getting a bit confusing now. We've lost a bit of readability here in order to get a more compact representation. But we need to do that via variables. So what on earth is happening here? Well, we have a state that has two possible self loops back to itself, but they do different things. Okay, well, they obviously have different guards on them, and they do different things. So what does it do? There's essentially an internal variable called count, which is going to count the amount of cars that go through. And if a car comes in, we're going to increment the variable, and we are going to set the output to be added to 1 immediately upon that transition. We have to bound it by something as well too. So we could bound it by some number m, right? We also bound it up, lower bound it by 0, so that if a car comes out and down is present, and it's above 0, we make sure count is decremented, but we don't decrement it below 0. And So we have a beautiful compact representation, but it's burying the concept of state and output through the variable all in one, which once again it loses a bit of visibility here to work out what's going on. You have to start digging into the actual equations here to work out what's going on. And that's because, yeah, as I said, the output is kind of sneakily using the count variable, the internal count variable there. Now, where could we use the count variable in a more complex state machine? I'll just show you. I'll just show you the general form now for extended state machines. Indeed, your state machine for the robot controller will need variables in there, in particular to measure the angle that it's rotated through or the distance it's gone since a last step of some description. Right? You might want to hit an object and then back up 10 centimetres and then turn 90 degrees. And they're all different states of what you're doing, but you need to keep track of those measurements. Right? So you need some variables to be counting those things. Okay? So your state machine would look something more like this, where you've got your usual guards and output actions, but you have set actions written underneath, just like as is in this example here. And it means from the sort of the black box look at your state machine, you have inputs and outputs, but you also specify variables as well that are used inside it. Okay, so it's just another thing to think about, right? We've got these internal variables and we can use to signal or keep track of events. All right. All right, and they didn't come in. Okay, so let's look at a more complicated model. Now, this is heading towards a sort of model that you may need to come up with, once again, for your Kabuki operation. This is the traffic light model, but this now takes into account the fact that we want the lights to stay in a certain state for a minimum amount of time, right? We don't want it to be purely event-triggered, event-driven, right? Because as soon as a pedestrian pushes a button, you don't want the lights to immediately go green or red or change in the opposite of what they are. So this is a modified model here where we've still got the three inputs, right? Sig R, Sig G, Sig Y. We've got an output pedestrian, but now we've got a variable count. And we start off in red, for instance, and you can see now that unless this guard is met, right, count greater than 60, what do? Well, we just keep incrementing count. This is a time-triggered model, okay? Why? Because count needs when is that little default transition taken? Well, when is it taken? It's not event-driven. It's taken on a clock edge. So this is a time-triggered model. So every clock edge, we're increasing the count. Once we get above 60, what do? Well, our output is set to, the SIG-G is set, and we reset the counter. So we go to green. While count is less than 60 seconds, we're assuming this is ticking at 1 second, one reaction per second. So it's taking that one reaction a second in order to build up the count. When we get to green here, right, as long as green's less than 60, we keep incrementing green in order to provide some reasonable time for traffic to actually get across the intersection. Okay, two things can happen then. So now we've got a slightly different state transition diagram here. We've got the case where a pedestrian has come along and the count has already, if you like, expired or something, right? It's got above 60. It's been sufficient time for cars to come across. Then what happens? It goes straight to yellow. So you immediately signal SIG-Y, so that's pure signal, bang, that goes to the output, reset the counter and go to yellow. In yellow, we keep basically counting here and once count gets above 5 this time, it's only a short yellow state, we go back to the red state. So that's that sort of loop here, right? It's a 60-second on red, 60 on green. If it's greater than 60, pedestrian pushes, go to yellow for 5, go back to red. What happens on this side? Well, the condition is slightly different. It's just if the count is less than 60 and a pedestrian has come along, then what we do is we go to a pending mode where we register the fact that there's a pedestrian there, memory. So pending means we know a button's been pushed, but we still haven't reached the timer value. And we increment the timer, right, the counter via a time-triggered reaction here. Once it gets above 60, we then go to the yellow state and then back to the red. So, yeah, this is an example of a time-triggered system now where there are variables that are helping us. Okay, and we also have, really 3 transitions out of the green state here that are clearly, the guards are clearly labelled. Yeah.
I don't think the pending is necessary.
You don't think
Yes.
the pending's necessary? So the issue is that pedestrian is a pure signal, it's not a persistent signal. So it's a momentary button. So you need to be reactive to that. Okay, it's not something that's externally latched and you always know that it's been pressed, right? So you need, even thinking about the transitions, you need to either immediately go to yellow or register the fact that someone's pushed a button and still wait. Okay? So there are 2 distinct states here. Register the pedestrians there and still keep waiting, or if you've waited long enough, directly go to the yellow. Therefore, you don't need that sort of memory, if you like, of a pedestrian press. Okay? So pedestrian, importantly, is a pure signal, but it's not a persistent signal. And it's true, you know, those push buttons, they come back at you, right? They're momentary things. So the state machine is basically providing a latch function almost, in that it's remembered that there's something, it needs to go to yellow. Otherwise, if no pedestrian comes along, stay in green, right? Why stop the lights? You don't stop the lights just on a cycle. Okay, in this case, and this is something we won't get into, in this case, count, it's a variable, but it also, because it's a time-triggered model, it's indicating timing. So that's something that's not present typically in FSMs. There's no timing data in here. How often does this get updated? How quickly can you get between the states? No idea. Not listed. But here, we are implicitly giving more information. We're saying this variable now can control the transitions between states, and it's obviously connected to some sort of timing generator. And if it decides to generate counts at 1 second or 1 millisecond, you can get very different state machine behaviour, right? Depending on what it's doing. So it's an external factor that we might have to consider. In particular, it's an example of a hybrid system. All right, so we won't be going into details about hybrid systems. It's chapter 4 in the textbook. But what we're going to do is we're going to look at examples where we can compose concurrently state machines together and have a hierarchy of state machines. Okay, so for instance, an example of that might be when we went all the way back to here and we assumed this little state machine here, which was hooked up via the SIG-Y, SIG-R, SIG-G and ISCAL connections to another state machine that looks like this. Okay, and how those 2 machines interact and being able to predictably show how they react is important, particularly for reachability and safety analysis. All right, so your goal for the workshops Friday and next week is to be able to start mapping out your algorithm for object avoidance. Okay? The first task of the project is to get around miniature brick walls. Basically, you hit a brick wall, right? That's going to be your input signal. It's a pure signal, right? It's a very simple thing. It tells you if you hit something, and then be able to then construct a state diagram such like this to get around it. Yes, up the back. You might have to yell out.
Sorry. What happens if the pedestrian keeps on pressing the light and the button saying that they're there?
I would argue that it would go to this state, right?
So would it just continually go there? Like,
Oh,
once there, what would happen if they kept on pressing it?
well, it doesn't matter. The only guard coming out of here is count getting above 60. So don't care if you hammer it. So hey, that's a valuable lesson, isn't it? Right? No matter how hard you punch those things, the state machine inside there's not going to listen to you. Okay, so FSMs, what you should be able to do with FSMs by the end of this subject, so that means, for exam, for instance, be able to represent a system, design and represent a system. But being able to represent the system as FSM means you can put it into a simulator that can generate all possible behaviours and tell you, uh-oh, you've ended up in a state where you shouldn't have ended up given those input conditions. It also, via non-deterministic FSMs, gives you a way to model the environment of a system without knowing information about it. You know the environment may trigger a transition, but you don't know on what conditions that may happen. And that's the non-deterministic FSM. FSMs are a specification of how something should work. So in Eng, right, we're really pedantic about specifying exactly how it works. And lastly, this will be later on in the course, we're going to look at FSMs as a way of checking that the system satisfies its specifications, it does what it should do in its particular operating environment. All right. Okay, so please read ahead for your next workshop for Friday or for next week. And in particular, start mapping out perhaps a very basic algorithm for object avoidance. It will help you immensely when it comes to programming the workshop, the Kabuki robot for the next workshop, next week or Friday. All right, we'll leave it there. We're going to talk about composition of state machines next week. So it's going to start getting complex.